Let's continue our discussion of the photoelectric effect and take a look at another example that uses the photoelectric effect equation. This is going to be a numerical example. In this practice problem, you're told that the energy required to remove electrons from the surface of rubidium metal is 208.4 kilojoules per mole. First and foremost, let's take that whole sentence and simplify it way down. What does it mean when we say the energy required to remove electrons? That is the binding energy. So that's all we can say is that 208.4 kilojoules per mole is the binding energy. That simplifies that down quite a bit. Now you're told the rubidium metal is being irradiated with 254 nanometer light. So that gives you the wavelength of the light that's being used. And you're asked to determine the maximum kinetic energy that each of the released electrons can have. You're given a conversion factor that allows you to turn nanometers into meters here. And so let's talk about how you're going to set up and solve this problem. Notice, as I mentioned a moment ago, when you're being told the wavelength of the light, that's going to be used to find the energy of the photon. So this is equal to the wavelength, and so we can use this to get E of the photon. Let's start setting this up. We'll begin by writing out the equation that deals with the photoelectric effect. Anytime that you are dealing with a problem where you're shining light on a metal surface and ejecting electrons, you want to be thinking about the photoelectric effect. And it helps to write the equation that describes the photoelectric effect so that you can see how the variables relate and you can kind of imagine what's going on. So we'll write that out. By writing it out, it gives us a good idea of what we're trying to solve for here. The goal of the problem is to find the kinetic energy of each electron that's ejected. We need to know the energy of the photon that's put in, and as I mentioned before, the wavelength will help us to find that. And we have to subtract from that the binding energy, and the problem gave us what that value is. What I'm going to do now is find the energy of the photon. So just in a separate color down here, I'll write for E photon, that's going to be equal to hc over lambda. That's an equation that we're just given here. And for h, that's just a constant, 6.626 times 10 to the minus 34 joules seconds. C is the speed of light, which is 3 times 10 to the 8th meters per second, over the wavelength, which you're told is 254 nanometers. And then you have to watch out for the units here, right? Because when you take a look at the units, you'll notice that, yes, the seconds and the seconds cancel out here, but on the top you have distance with units of meters, and on the bottom you have it in nanometers. So we have to make them compatible. It doesn't matter if you convert the meters to nanometers, or if you convert the nanometers to meters. It doesn't matter, as long as you have both with the same units. Just because I have more room on the bottom, it'll be easier for me to convert the units of nanometers into meters. So what I'm going to do now is say, from our conversion factor, 1 nanometer goes on the bottom, so that cancels, is 10 to the minus 9 meters. That cancels out the units of nanometers, and now the meters cancel as well. And at this point, all the numbers can be plugged into your calculator. And when you do that, you'll find that the energy of the photon that's put in comes out to 7.83 times 10 to the minus 19 joules. So now we have that, and we can plug that into our photoelectric effect equation. We have the kinetic energy of the electron ejected is equal to the energy of our photon that we put in, 7.83 times 10 to the minus 19 joules, minus the binding energy, which you're told is 208.4 kilojoules per mole. Now, before you can subtract the two numbers, you should look very carefully at the units here, and in order to add or subtract numbers, they have to have the same units. We recognize that they're not the same. One is in units of joules, and the other is in units of kilojoules per mole. So we're going to have to fix that here. So first I can convert the kilojoules into joules, and so I'll do that by multiplying by 1,000, because there's 1,000 joules in every kilojoule. However, we're still not done yet, because although the kilojoules have been converted into joules, we still have the units of per mole, right? So for the first term, the energy of the photon, we have that is in units of joules. The second term is in units of joules per mole, and those two units are different from one another. to see how they differ from one another and how you're going to make the units compatible, it's important to think about what these things represent. When you calculate E photon from this equation, E equals hc over lambda, what this represents is the energy of a single photon. Similarly, when you're doing the calculation of Ke electron, that's telling you the energy of a single electron, right? That's why in the problem they're saying, what's the maximum kinetic energy that each of the released electrons, right? That's each and every single electron. So that's what Ke electron represents, is the energy of a single electron. However, when you look at the binding energy that's been given to us so far, that was in units of kilojoules per mole. So that's saying that you would need to put in 208.4 kilojoules of energy to remove 1 mole of electrons, right? Not a single electron. This is for a mole of electrons. And so now, by recognizing that, we can see the differences between these numbers, right? This number deals with a single electron. This number deals with a single photon. This number deals with a mole of electrons and photons. So to make the units compatible, we have to convert the number that we have for the binding energy so that instead of talking about a mole, we have to talk about individual photons and individual electrons. What is the conversion factor that goes from a mole of something to just individual items? Remember, that's Avogadro's number. So we're going to need to use Avogadro's number to get rid of the moles. Avogadro's number tells us that 1 mole is 6.02 times 10 to the 23 items. And now I knew to put the moles on the top so that it cancels the per mole in the units of kilojoules per mole. It's again why it's so important that you make sure that you're writing out the units so that you're putting the conversion factors in the right place. If you didn't do that and put Avogadro's number in the wrong place, your answer would be off by like 46 orders of magnitude, which is like a lot of orders of magnitude. So be aware of that. The moles cancel out, and now all I have for energy units is joules, right? This is the joules per individual item. What I'm going to do is just evaluate what this number is after doing the conversions. So the kinetic energy of the electron will be equal to the energy of the photon, which is 7.83 times 10 to the minus 19 joules, minus, and then when you plug all this other stuff into your calculator, what you find is that the binding energy in units of joules per photon is 3.46 times 10 to the minus 19 joules. All right. By doing that, it's kind of nice because then I can kind of explain one more time what the kinetic energy of the electron is going to be and how the photoelectric effect experiment works. In this experiment, we're putting in light that has an energy of 7.83 times 10 to the minus 19 joules. That's how much energy is coming into the system. It costs us 3.46 times 10 to the minus 19 joules to remove an electron, right? That's the cost of removing the electron. So when you subtract that from the energy that's put in, whatever's left over is the excess kinetic energy that the electron will be released with, right? That's like the change that you get back when you buy something at the store. So the kinetic energy of the electron, like that leftover energy, is going to be equal to 4.36 times 10 to the minus 19 joules. And there we have it. There's our answer. It's really important for you to go back and practice this one again on your own. And when you do it, make sure that you're writing out all of the units so that you get the right answer. There are a lot of common mistakes that students make with problems like this, and almost all of them relate to unit conversion issues. The way that you avoid those mistakes is by writing out the units and showing how all of them cancel. Now, Einstein did the experiments associated with the photoelectric effect and published a paper that explained it back in 1905. He actually published 4 really important papers in 1905 when he was only, I think, like 26 or 27 years old. It's remarkable what he was able to do at such an early age. I'm like in my mid-30s, and I feel like I've barely done anything with my life in comparison to Einstein. But then again, I mean, he's Einstein, right? So I probably shouldn't be too upset if I haven't accomplished everything he has yet. Now, in this paper, right, by describing the photoelectric effect, Einstein provided further evidence for the wave and particle-like duality of light. And this discovery was so important to our understanding of the nature of light that Einstein was awarded the Nobel Prize in 1921 for his work on the photoelectric effect. I think it's kind of interesting. A lot of people might think that Einstein got his Nobel Prize for the theory of relativity or for like E equals mc squared, because I know that he's most well known for those things. But the work that Einstein received his Nobel Prize for, that he received his recognition for, was the work that he did on the photoelectric effect, because it was so important in developing our understanding of the wave and particle-like duality of light. Now, after winning the Nobel Prize, where would you go to celebrate winning a Nobel Prize? Maybe you'd come to Santa Barbara. This is a picture of Einstein at the beach. He's at Butterfly Beach down by Montecito. In 1933, he came out here and visited. I think it's kind of cool to see this picture, to see that there's a connection between Einstein and our local area here. I don't know. Whenever I go to the beach here, I like to think that I'm like breathing in the air that Einstein breathed, and maybe it'll make me smarter. It hasn't really worked yet, but maybe someday it will. I don't know. It gives me more motivation to spend more time at the beach, I guess. One more thing that's worth mentioning here is that at the time when Einstein did these experiments, the photoelectric effect was something that helped us to understand the theory, right? It helped us to understand the wave and particle duality of light. But at the time, maybe there weren't a whole lot of practical applications for it. But that's kind of how science kind of works. Initially, a lot of the experiments that you do might not have very obvious practical applications, but over time, you begin to develop some. So let's talk about an example of a practical application of the photoelectric effect and where we would see it in our everyday life. One place where the photoelectric effect is used in our everyday life is in elevator doors. So as you might be aware, in an elevator door, if the door is about to close and you stand in the threshold of the door, there is some mechanism that prevents the door from closing, and in fact it causes the doors to reopen so that the door doesn't close on you and kill you. The way that it works is by using the photoelectric effect. So what happens is, shooting across the threshold of the door is a laser light. On one side, you've got the laser light. The beam shines across the threshold. And on the other side of the threshold is a detector. This detector is just a piece of metal that, when hit with the light of the laser, will eject photoelectrons. And as those electrons get ejected, it generates an electrical current. The flow of electrons is electrical current. This electrical current sends a signal to the electronics inside of the elevator, telling it that the doorway is clear, and so it is safe to close the doors. But if someone steps into the threshold of the elevator door, that blocks the laser light, and that cuts off the light to the detector. That causes electrons to stop flowing, right? To stop being ejected from the detector, and causes electrons to stop flowing. And that sends a signal to the electronics inside of the elevator saying, there's something blocking the doorway, do not close the door. And that's how you're able to be kept safe. So I think it's nice to see how sometimes even experiments that at the time seem very abstract and maybe they don't have practical applications, over time you end up finding important uses for them, things that we use in our everyday lives to help make our lives better and to help keep us safe. That brings us to the end of this video. And next, we're going to talk about the wave and particle duality of matter.